Okay, our next presenter is Robert Sparea. Sorry, Robert Palin with Sparea.
Hi, everybody. Can you hear me okay?
Yes, I can.
Excellent. So I am calling in remotely from a very wet and windy Los Angeles, which probably sounds like something you would never expect it to hear. But I think kind of further justifies why we're all here today talking about ways to prevent or limit climate change. This is a very, very almost spooky experience, especially for this time of year. But I'm here today to talk about something that may be a little bit contentious for this crowd, which is really to take you on a journey that we've been on in trying to find a sustainable solution to climate change for shipping. And it's kind of led us around in a circle to how we think the solution to decarbonization may actually be within carbon itself. So you may see I have the bit of a joke of a subtitle. I'm a big fan of the Dr. Strangelove film. If anyone remembers that. That worryingly remains as relevant now as it ever was, I think. So first thing will be to introduce myself and Sparea as a whole. So I've come from an aerodynamics background, primarily with road vehicles and racing cars. Worked on everything from actually bicycles and people, clothing for Olympic athletes, all the way up to semi-trucks or lorries for the Brits, and Formula One cars. During my time on electric vehicles, I was at Tesla and became somewhat radicalized in the, or an EV angelist, as they say. And I got into a lot of conversations with people of differing views on the true impact of electric vehicles, things like the long tailpipe argument, if anyone's familiar with that, where you're just moving the problem somewhere else. And one of the things I really wanted to do was not be greenwashing things. So I dug into some of these things and realized that everything has a footprint, often very, very many footprints in different areas. And I wanted to try and make sure, make sure that we were being as true to the intent of Tesla, which originally was to make road transportation sustainable. So I looked into all the areas, and two that really stuck were the logistics side and moving people and materials around. That broke down to shipping and aviation. Aviation is a big technical challenge, difficult to decarbonize. Excuse me. But shipping is one where I thought we have a lot of tools to our advantage. And thinking back to once upon a time when shipping was completely decarbonized, when Columbus and Cook did their sailing around the world, they used no carbon fuels. So a little while ago, I started up Sparea with the view of applying some of the learning that we had from the electric vehicle world and motorsport world to shipping and to decarbonizing shipping specifically. We managed to recruit along the way a few, I suppose you could call them conscientious objectors from the oil and gas industry, who realized that they might not be helping as much as they could. And we set about trying to first understand the problem and the challenges, and then see if there's anything that can be applied from across different industries. Because something that we saw, especially at Tesla, was a lot of the challenges we faced had already been faced by other people in completely different applications sometimes. And we could shortcut our way to solutions by learning from them. An example that comes to mind is the production line for the Tesla Model 3 was actually heavily inspired by Coca-Cola and NVIDIA. So Coca-Cola make tens of thousands of metal cans at a hell of a rate. And and with quite good precision. And NVIDIA make complicated electronics equipment, again, in large numbers and with great complexity. So a Tesla car is a big metal can with lots of complicated electronics in it. So there was a lot to learn from how these other companies approach those tasks. And it's really a difference of degree rather than kind. So there was a lot of shortcuts we could take to improving the process. We wanted to see if we could do that for ships. So some of the stuff I was going to talk about was actually being covered by other speakers this morning, and a bit better than I was going to as well. So I will speed through some of this. I can ask more questions in the Q&A section at the end if I go too quickly. But I realize most people are aware of the general picture. Shipping's pretty much using exclusively fossil fuels. We know that fossil fuels cause environmental damage, often long-term environmental damage that we need to at least minimize, if not completely eliminate, because of the way the Earth's biosphere is responding to these inputs. Something that is evident when looking from the outside is that the shipping world seems to be very much focused on just changing one piece of the puzzle. It's really a question of what do we burn instead? And that, I think, is not a good way of framing the question, because if you only change one piece of the jigsaw puzzle, the piece you put back in has to be the same shape. If you remove more of the pieces, you have more flexibility to change the overall picture. And the last thing is what I was just saying about how we really want to look at the situation with fresh eyes. Of course, there's going to be lots of times where we suggest something that's essentially reinventing the wheel, or whatever the maritime equivalent of that would be. But I know from spending some time working with people at SpaceX, they have a philosophy where they bring together fresh graduates from university with lots of new ideas, lots of new ways of looking and thinking about things, with old veterans who've spent their lives working in the industry, who've tried a lot of things and know what will work and what won't work. They put them together, and there's a really a good dynamic, surprisingly healthy dynamic, where a lot of the kind of but why questions get answered until eventually there's the that might actually be different now. The technology is different, the understanding is different, the resources may be different, and so many things so many best practices and traditional understandings of way of doing things turn out to be really down to some particular set of circumstances that isn't really applicable anymore, but it's just become the standard. So it's worth kind of lifting up every rock to see, would we do things the same way now, given the same challenges? So when it comes to shipping, we looked at it from very much first principles, and you'll have seen this picture once this morning and explained better and in more detail by Guillaume. We're looking at fundamentally moving goods from one place to another, which requires energy. The questions are, where do we get that energy from? How do we access it from where it is? How do we move it to where we need to use it? How do we actually make use of it when we get there? And then what is the means by which we employ that energy towards our goal of moving goods? As we saw, there's an awful lot of complexity in each of these different sections. It's definitely not a trivial problem. But when we looked at it, we tried to think of it in a long-term view. And so this issue at the top of environmental impact and resource depletion becomes really quite important. You can't do something that's sustainable if it's constantly running out your resources and or damaging the place that you're trying to live in. So when it comes to sources, this really kind of rules out fossil fuels as any kind of future option. Arguably, biomass we can keep regrowing plants, but that has large consequences for land use. Waste is also a problem there because it rots and causes methane, so it's sometimes worse than you would think. There's also large water consumption, which is another precious resource. Materials, yep, it's always going to be a concern. We need to be able to reuse materials as much as possible. The only real source of energy that is truly endless is renewables, accepting the idea that the sun will eventually burn out. So we realize that long term, everything's going to have to come from renewables. So we will essentially have to harness and make our own fuel one way or the other. So this is the long-term image. We need to be able to create our own energy with minimal impact, or create and use energy with minimal impact. So we created our own decision matrix of where are we right now? What sort of options do we have for energy? And we created this this matrix, which I have to say we agonized over, and this is probably version 2000. And certainly, I'm sure everyone in this room looking at it will have their own rating system and question particular ratings we've given different things here. We did as well. Like I say, this has been churned over so many times. I don't want to linger on it too much because of that. It could definitely soak up a lot of time just trying to understand why is a certain thing given a certain rating. It's not too important, I think, for the moment, because our question was, okay, this is where we are, where are we going? And so we looked at what is the future and what would be the path to get us there. And we evaluated each of the different options. We actually came to eventually methanol being the least harmful of the different options, but we were very concerned that it's a carbon-based substance and we're trying to decarbonize. So we had to really sort of double check our sanity here and go back through the loop of, are we sure this is where we're going? Are we sure this is how things will evolve? And we started to question, well, what are the things that drive that evolution? And we basically narrowed it down to 4 general categories. One was technology, another was economics, another was politics, and the last one would be regulations. And I think the more cynical members of the audience might be wondering if those last 3 are actually separate at all. So we were very mindful of how regulations are the channel through which all of the other factors really influence the evolution of the ecosystem. And that pushed us to looking at how are regulations formatted and what are they actually trying to do? How are they driving the evolution of the system? And something that I'm not sure if everyone's familiar with, the idea of a global warming potential. This is a way of condensing all of the various bits of complicated chemistry and physics that go into a substance's influence on climate change and normalizing, simplifying it into a single number, and then normalizing that number based on the impact of CO2. There's so much complexity in that, though any one number is always going to have a lot of caveats and limitations. And indeed, there are at least 2 different formulations of GWP. One is over 100 years. So what is the impact of these emissions over a 100-year lifespan? Then another, which is gaining a bit more traction, is the GWP 20, which is the impact of things over a shorter time span, because there is a general assumption that we're on a trajectory to reducing our emissions in general. And so further down the line, we should be in a better position. But right now, what are the main priorities to have the biggest impact right now to kind of buy us time for that slower transition? So the GWP 20 figures, as you can see, are often significantly higher. And that changes the landscape a bit, and also, I think, focuses the mind on how much we need to do quickly. With the idea that regulations they're a forcing function for the evolution of a system. And I think language is also a key part of that. And it came to the conclusion that we don't really think decarbonization is the right language, largely because it focuses on one element, which, as we can see here, is by no means the biggest or the most potent driver. In terms of absolute quantity, yes, but there are many things that we are emitting that are worse in their individual contributions, and they don't seem to be really a focal point. So we looked at the regulations, and we've recently had the EEXI, EEDI, and CII come in, which are a great attempt to enumerate at least the current situation and provide some kind of driving force towards where we want to go. But then you look at the formulation of them and they are focused entirely on CO2. Now, we within SPAERA looked at this and thought, this doesn't seem to make sense. You're missing large parts of the problem. So you're not going to drive the system to a satisfactory state. So we were trying to formulate, well, how would we change this? And we thought that the CO2 conversion factor should really be changed to account for the different impacts of the various constituents of emissions you might have. It isn't just a case of what type of different engine do you have. It's what are you burning, or what are you consuming, and what are you releasing into the atmosphere. This, I was a bit worried about this because I was looking at this and thinking, if I'm going to present this in front of a bunch of knowledgeable people, I could get shot down if I've misunderstood it. So I fired it across to a friend of mine at the ICCT, the International Council on Clean Transportation. And he said, it's funny you should ask this. We're just about to release a paper on this very thing. And they did a much more robust and in-depth analysis of these various considerations and came out with more true comparisons of the actual GWPs, the global warming potentials of the various fuels and how they're used. Now, they did focus purely on carbon containing fuels. They didn't include ammonia, which I would have liked them to do. But it just goes to show, you can see in this table here, that the actual effects can be significantly more than you would think once you take into account all of the other emissions. So CO2 is a part of it, but there are other aspects in there as well, which give an equivalent, a higher equivalent CO2 contribution. This also gave us some confidence that we were along the right lines with methanol, because it did come out as the least harmful of all of these. But it really kind of paints a bleak picture of, even if we reduce or even if we switch to the least harmful of these, we're still doing quite a lot of damage. And there isn't a truly, I would say, sustainable path forwards. Like, all of these numbers are greater than 1. And we need to be closer to 0, frankly. So we thought, how do we just consume less fuel? How do we reduce the amount of emissions, even if we can't improve the method of harnessing energy? How do we just use less? And we looked at the way there is an understanding now that a ship will leave its port with all of the energy it will ever need for its journey, plus sea margin, plus some conservative estimates for emergencies and unforeseen circumstances. Now, this is a complete contrast to the olden days, where we didn't have any stored energy. We would just leave port and harness energy along the way. And this mentality of kind of overwhelming nature appears to have come up around the time of the Industrial Revolution. There's probably some good sociology or politics papers that could be written on it. This idea of we dominate the natural world with our powerful sources of energy and machinery. I think we need to get back to the idea of working in harmony with nature a little bit more, and at least not turning our backs on the abundant sources of energy that are right there in front of us, and not considering bad weather to necessarily be an obstacle, but an opportunity. All of that stormy weather is energy in the system. Can we make use of that rather than just trying to fight it? So we came up with a concept of a ship and a ship powertrain, which wouldn't rely on fossil fuels at all, but would instead use some stored energy in the form of methanol, which we would utilize through fuel cells, where we would at least be able to control the chemistry. Ultimately, burning a fuel is just oxidizing the hydrocarbon. In this case, we can do that in a more controlled manner than kind of throwing a match into a bucket and hoping that the resulting boon goes the way you want. Apologies to any engine developers who will say that what they do is far more complicated than that. But a fuel cell just gives us the option to be more precise with our chemistry. We can make the ship more efficient. There are many ways of improving efficiency. It's a pet hate of mine coming from the car industry, where you're always after, and certainly the motor racing industry, where you're after tiny, tiny fractions of a percent. In fact, we once had a department in Formula One that was known as the Department of Marginal Gains. And it was just adding up every sort of 0.1% and seeing what you could get if you achieved all of those. And then when it comes to shipping and public claims for new generation of ship, or how we're going to get to IMO 2030, IMO 2050, we're going to have a 5% efficiency improvement from the hull, 10%. Those are huge. If you still have 5 or 10% kind of on the table, what were you doing before is a question. So either maybe those gains weren't taken for some other reason, or yeah, there's plenty of opportunity out there, it seems. Yeah, we'd also make use of wind through sails, or some version of sails. And then we would have stored energy for a battery, because if we have electricity as a common energy medium on board the ship, a battery just helps to smooth all the inputs and outputs, and also can be used for cold ironing or maneuvering in and out of port, where you perhaps don't want to fire up your larger powertrain. And we'd have solar, because why not, frankly? As living in California especially, it's very apparent to me, other than today, that we should be making use of this free energy that rains down on us every day. So we thought, we did all the math behind this and figured that we could satisfy the energy requirements of our ship. But there's the question still of the economics. This all sounds great, but is it going to cost a lot? Well, we figured that we can improve the efficiency. We can get energy from the wind, we can get energy from the sun, potentially we can get energy from the waves, as we saw in an earlier presentation, and we can store some energy in the form of green methanol. That puts us roughly competitive with current heavy oils. These prices are a little bit off now, because I basically stole the slide from an earlier presentation we did. But this brought to mind a conversation that came up a lot in the electric vehicle world, which is the idea of these hidden costs. It's like, well, if you think you can make it match, but what are you hiding? What are the extra costs that you're not including? And when we looked into that, really, it's on the other side. Fossil fuels have huge amounts of hidden costs that are externalized and effectively subsidized by society. The details of how we got to this $1,200 per ton is on our website. There's quite a lot into it in terms of direct subsidies, indirect subsidies, costs in public health, disasters, insurance, all these things. Those are not paid for by the people who consume the fuel, but they are clearly costs borne by everybody for that use of that fuel. And we want to have a situation where that is not a dynamic in the system at all. One consequence of that, which we don't know if we'd ever be able to realize, but we're hoping, is that if we can harness energy from the environment and reduce how much stored energy we use in total, then we can change this balance between OPEX and CAPEX for ships, which currently drives that ecosystem towards making fewer really, really big ships, because the OPEX just dominates completely over everything else. If the OPEX is dramatically cheaper, then maybe we could have more ships running at a lower price and still achieve the same mass flow of goods from one location to another. I notice in the corner here, I have this CC in red, which is something I've kind of skipped over so far, which is just, we have methanol. It uses, even if we source it from a green origin, we still end up with CO2 at the end of it. We run it through a fuel cell, we still output CO2. So what do we do with that? Well, we can capture it and store it, but then do we try and bury it underground or turn it into some kind of long-lived plastic product? Or do we put it back into the system and make more methanol out of it? Now that seemed to make the most sense to us, in that we have a resource and we've used it, we want to reuse it. Rather than going and getting some more, we already have it. Why would we not reuse that? So this is something that, a general concept we want to apply to all materials to do with our project, which is we consider ourselves not as consumers or users of things, but rather temporary stewards of them. I mean, in the largest sense, all of the materials that we have and use in our daily lives have been on Earth for a long time before us and will be on Earth for a long time after us. So we always are just temporarily interacting with these things, but they'll be here long after we're gone. So we thought, okay, we're going to have carbon. We want to reuse it. We're going to create green methanol, produce CO2 and a small amount of water, which are the raw ingredients for methanol. So can we just reuse that methanol again? This led us to the idea of a carbon battery. We're trying to figure out a better name for this, because C battery seemed a bit too cheesy. It's C for carbon and C for ocean. It made everybody groan, but it works for now. But our idea is that, in an analogy with an electrical battery, where you store energy kind of by shoving in electrons, so negatively charged particles go into your battery and store your energy. We're using hydrogen, which is basically a proton, so a positively charged particle. We add it to our carbon, we take it back out in the fuel cell. So why don't we add it back again when we're done as a recharging process? So we've come up with this circular loop of, we can use green energy to create green methanol. We then put it on board the ship. There we go. We put it on board the ship. We put it into the fuel cell. It outputs a mixture of water, CO2, carbon monoxide and hydrogen, which we can then loop back and reuse in the fuel cell again until everything is fully oxidized and we only have water and CO2 on the outside. We can capture that carbon, compress it, bring it back to base, put power and water, well, put power in first to reduce the CO2 to just CO, so syngas, basically. And then we electrolyze the water that we have, put that back in as well, and we get methanol again. So we have this loop where, in theory, we could be using the same individual carbon atoms forever, with the only inputs being electricity, which we can get from renewable sources like solar, wind, geothermal, water and CO2 are the only inputs, and yet we get useful power out. We would still need to lean very heavily on wind power to get us over very long distances, due to energy density and storage volume on the ship, but that's entirely feasible. So it's not really a big limitation. Now, that all sounds very nice in principle, but how are we actually going to achieve that? And this is kind of hot off the press because we've been preparing for an application for a grant from the UK government to build our first prototype. And every time we talk to someone, they introduce us to someone new and say, hey, you need to talk to these guys. They're doing that part of what you're doing. And they have a really cool, neat way of doing it. So for the last few weeks, every day we've been churning around our plans as we kind of insert a new building block into our process. But we're set now, and we think we have all of the pieces in place to create green methanol, use it in a low temperature solid oxide fuel cell. So it's still warm, 400 Celsius, but instead of 800 or 900 Celsius fuel cell, that gives us we don't need a reformer for that. So we can go straight from methanol and water, no additional combustion, reforming, no nitrogen, oxygen, any other products at all. We recycle any carbon monoxide and hydrogen that hasn't been used, so we can make sure it all gets fully oxidized. That the CO2 that comes out gets dried, we separate the water from it, we compress the CO2, and then we can bring that back. And we're working with 3 universities on a system where they will convert that to syngas and then add electrolyzed water to create hydrogen to complete the loop back to methanol to go back on the ship. Now, this doesn't necessarily mean that we would use the same carbon atoms forever, but it's more likely that it will be, I think fungible commodity is the right term, but the logic is there that we don't need any new material. We will have everything we really need within that loop. And I see that as being a key part of being truly sustainable. We don't need to use any additional resources. We can just reuse what we already have. So that is the pieces of our puzzle that we're trying to fit in. And the long-term goal is to make our own ship. The idea is a full-size car carrier, primarily because we're heavily influenced by the car industry and want to make sure they have a zero-emission logistics chain. It is always very sad if you create a green vehicle and then burn oil to get it to its destination. So we want to be able to have a zero emissions chain there. But the technology doesn't necessarily, it's by no means limited to this application. We can fix our wind power system onto many different types of ship. We'll have electrical generation capability, zero emission electrical generation capability that can be applied to auxiliary engines or main engines, possibly cruise ships even, although with their very large hotel loads, they're a big challenge. But it could be modular and used in many different applications. We just think that there is a solution to the decarbonization challenge that is available now, or at least the principles of it are available now. If we change our minds from the idea that carbon is the big bad and we need to never be anywhere near it, it's actually a really useful, flexible medium for storing energy. And ultimately, we're all made of carbon. So a decarbonized world would be pretty quiet and a bit lonely. So we think that it shouldn't be demonized quite so much, and it can actually be a way out of the problem we've got ourselves into. I should just notice that our project is currently nicknamed Project Lovelock after James Lovelock, who wrote the Gaia hypothesis, a scientist who studied ecosystems on Earth and the interplay and relationships between them. It's very sad that he died this year and seems to have kind of disappeared. There's no foundation or anything to follow on his work or his share his wisdom. So we want to name our project after him to honor him. So that's it for now. I imagine there's going to be quite a few questions, so pass it back to the team at the web auditorium to mediate that process.
Paul, go ahead.
Very full lot of institute and technical information resources. Very interesting concept, this sleep battery. The question is, especially in the example you have of a prototype vehicle carrier, vehicle carrier is most certainly going to be volume limited. Is there any reason to not have a 100% C battery powered car carrier? I'm all for sail power, but is it absolutely necessary?
Why not? It's free. It seems to me to be wild not to use it.
That's very inspirational. I agree with it, but again, I'm just curious from an engineering point of view, would it be possible to have that same ship running just with sea battery?
Quite possibly, yes. Car carriers are a little bit of a soft target for us in a way because they are very low density cargo ultimately. So you don't have such a deep draft. It's low resistance, and especially with the slow steaming becoming more normal at the moment, it brings you down into the realm, the speed where wind can be a bigger proportion of it. So it allows us to just use less and less stored energy.
Yeah.
You're talking about developing a new carbon powered fuel system and also a new sail technology. That's not typical. We don't typically see startups do those two things at once. That's the vision I have. Oh, and the ship. I forgot how all these ship.
It's I think because of several members of our team have aerodynamics backgrounds, and we've spent probably an equal amount of time cheating the wind by making low drag vehicles and enlisting its help to push racing cars down to the ground. So it's a little bit like the old saying that when you're holding a hammer, everything looks like a nail. We just think that aerodynamics should be a big part of this. The wind did work very well for ships for a long time, so we should take advantage of it as much as possible.
But why not buy a sail from Tech or one of your
So as a little bit of sort of history, we started off with a different company name, and the idea was to do just something like that, was to develop not so much a wind-assisted propulsion system, but power generation so replacing auxiliary generators with wind power generation using kites. But looking at the various competitor systems out there, it just became really obvious that there are many good options already, and they weren't getting any, ironically, traction within the market. So we looked at it, and to us, it resembled a situation where traditional car companies started to make electric vehicles by just removing a few bits from their existing car and throwing batteries in the space. And generally, as electric cars, those vehicles suck. There was a really big difference in designing a vehicle from scratch to take use of a different powertrain. And that's something that we see also possible in ships. Kind of something that was mentioned this morning was if you have a traditionally powered and engineered ship that you're suddenly using wind power on, you might be making a lot of leeway, or that hull is now not very efficient at all. So even though your energy is free, you're not getting the maximum benefit from it. So would we design a hull that is designed to travel with leeway rather than straight ahead? That's also something else that's come up a lot with cars, because typically in aerodynamics, people develop cars zero yaw. I think of crosswinds has been a rare thing, but at Tesla, we measured the wind experience by a car across many millions of miles and discovered that the car is almost never not seeing wind. And so we started to optimize the car for windy environments, which is also why Tesla's drag figures don't seem as good compared to the competition anymore. They're not what you see in the headlines, but the car will use less energy more of the time. So we want to apply that same kind of logic to the design of a ship rather than just bolt our stuff on and hope it works. That's a very negative way of putting it. That's not as bad as that sounds.
Yes.
So congratulations for the concept, putting all together the solution. This morning, when Marion made their presentation, for me, one of the key topics that there is more to develop, significantly more to develop than the IC, right? So one major question is that most of those technologies, they are significantly heavier, volumetrically challenging. So to make a ship that can put all the things together is a real challenge. So how you are addressing this, and second, what's your time frame? So when you expect to have something available?
So for the mass, some of it I think is partly because of the industry. Everything is made extra robust, which has some good reasoning behind it. But also, the way to make something robust isn't necessarily to make it bigger. We've been through some iterations of wing sail design, which they only did basically one FEA analysis, one structural simulation loop to try and reduce weight. Whereas for most car components, that could be easily 1,000 to 2,000 loops of that. Because if you're going to be making 1 million instances of an object, you want to make sure that you've minimized the amount of material that's used in there. And especially if that object is mobile, you want to minimize the mass and cost and everything. So I think the automotive industry, and especially motor racing, puts an awful lot more effort in absolutely optimizing things to such a ridiculous extent. That doesn't seem to apply as much in shipping, especially on some of the applications we've looked at, like the heavy bulkers, and we're looking at a aerodynamic device that may weigh several tens of tons, and they're saying that's fine. The ship weighs 200,000 tons. That's insignificant to us. It's like, it's insignificant to you, but it's still, coming from a racing background where there's no way you would have something on a racing car where the biggest load that an aerodynamic device ever experiences is its own inertia. That seems crazy. And I think for sure cost comes into that, but there are ways of manufacturing things. There are ways of optimizing structures that aren't really applied. And it goes down to even things like looking at the batteries. We've been shopping around for Class Society approved battery storage systems, and the energy density of the pack level there was, I think it was about 13.5 kilograms per kilowatt hour, I think. And yet in a current Tesla, it's about 4. So the question is, well, why is it so much different? And it's, they cannot tolerate cell runaway at all, okay? But a car battery is also designed to have other cars crash into it at high speed and to survive that. So there's an awful lot of additional robustness built into those systems, and hopefully no one will crash into your ship, not in a big rig or something. It might happen, but I don't know if you design the battery for that situation. But it seems like there's a lot of scope to reduce the mass, the footprint of these systems using, again, this kind of cross-industry perspective of how are other people making them lighter, completely fire resistant, or, it's certainly a very important criteria, because there's going to be people directly above your battery. You need to make sure that it doesn't catch on fire. I think that concern is shared equally with the marine world. So the pack level masses should be not too different, I think.
Okay, Rick?
Robert, there's a truism that if you start with a flawed assumption, you can't come to a correct end either. And you keep referring to Formula One racing as if it's the test bed for all the improvements that occur in engineering. I'm sure you're aware that there's also such a thing as sailboat racing, right? And that those people are not stupid either. And they're also looking for percentages, so speed increases that are even measurable. We've been doing it for longer than the car industry. So what makes you think that your aerodynamics and what you're thinking is actually going to fly in a way that naval architects actually have never thought about?
Primarily, so on the racing side, yes, it's more when you get that to the industrial side. And it's not to belittle the other side, it's primarily just focus and again, the forcing functions. If in a racing car you need to, or a racing yacht, you need to absolutely minimize mass, but if you have something that's already hundreds of thousands of tons, it becomes a very low priority compared to simplicity of manufacture or servicing or other things like that. I did once have an argument with some people in Formula One. They were belittling I think it was a Toyota Camry or a Honda Civic for how like primitive its engineering was compared to this fancy Formula One car. I said, yes, but that car costs $20,000 instead of 20 million. It can be assembled by a guy with minimal training at 2 o'clock in the morning on the third shift. It'll last a whole year with minimal servicing and yet be driven across Alaska or Texas. That is not an insignificant engineering challenge. I think it really depends on the application and, again, what constraints are people working to, but something we saw time and time again with Tesla, and including applying that to F1, they wouldn't believe that anything that wasn't F1 was worth considering. It's actually why I have a bottle on the wall behind me of unductable air, because I wanted to duct some airflow, and they said, you can't duct air. You really can. I said, no, it's not a thing in Formula One. And it was around the next year that the F duct came in and proved everybody wrong. But yeah, so there's definitely, I wouldn't call it an arrogance. It's more a case of reviewing assumptions to see if they're still valid. And that applies when we are talking to yacht racing companies, America's Cup developers, using some of the same tools, the same optimization logic, because the wisdom is already there. It's just not necessarily being applied. That's my larger point with all this. We don't have to invent some magical new technology, wait for 10, 20, 30 years until the tech is ready. We have all the tools available to us now. We just need to assemble them perhaps in a different way than has been done before.
Thank you.
Yes.
Yes, Robert, we talked before, and you touched on that very slightly, the digital twin.
Mm-hmm.
I still have personally, and that might not be shared, but a hard time understanding what it is and what it brings. So would you be able to elaborate a little bit?
Yeah, it's very common in, I suppose, land-based vehicle engineering now to have a digital twin of a vehicle. It's not like not necessarily an individual kind of virtual reality version of the object. Sometimes it can be, but it may be a collection of individual models. Maybe there is one that represents the geometry, one that represents the electrical circuits, one that represents coolant or liquid or gas flow circuits and systems, how they all play together. And it will be inside the computer, there will be a replica of everything that the vehicle is and does. That makes sense? And certainly for the case of race cars, they'll have the driver go and sit in it looks like a computer game, and they'll do 1,000 laps of a new circuit, testing out all sorts of different parameters on suspension, aerodynamics, and other things, so that when they get to the real race, the car is already 95% set up for it, and the driver knows how it's going to behave. So from the first lap out on track, they are very close to as fast as they can get. We do the same thing with cars like Tesla. I don't know how much it is revealing the secrets, but there's a team in the basement of the headquarters that do all this stuff to the most absurd degree, including, if anyone's watched the movie Apollo 13, where they get to the stage where they need to turn the spaceship on with using the minimum amount of power. So they go through all these routines of what happens if we turn this on first and then that on first. That is how Tesla work with the cars. So they capture every single watt and every single watt hour available power and energy that is used within the vehicle and make sure that they account for everything and optimize everything before the vehicle is even made.